All right, so let's work with an example using Rolle's theorem. So we are told to find the two intercepts of f of x is equal to x squared minus 3x plus 2, and to show that f prime of x is equal to 0 at some point between the intercepts, between two intercepts. Now, the way that this problem is given to us, we have to be a little bit careful. We are first told to find the first two intercepts. We are given the function f. We are also asked to show that the derivative is actually of x is actually equal to 0 at some point. It could be 1 point, it could be 2 points, it could be 3 points, it could be 10 points between the two intercepts. So here we will be applying Rolle's theorem. Now, the first thing I want you to note is that f of x is equal to x squared minus 3x plus 2, which is a polynomial. Polynomial functions are continuous on their domain. So this function is continuous on its domain. Also, because f of x is a polynomial and is continuous on its domain, we also know that f of x is differentiable at every point in its domain. We covered this a while back when we spoke about the derivative. So now we have checked two things from our hypotheses from the theorem. F of x is continuous and f of x is differentiable. Now, we have to find out whether f of a is actually equal to f of b to be able to solve this problem. However, notice that we don't know what a is, we don't know what b is. We are told that our a and our b will be the two intercepts. This is what we're told, because we're asked to find out when the derivative is equal to 0 at some point between these two intercepts. Okay, so let's actually figure out what the intercepts is. If you remember from pre-calculus, to find the intercept of a function, you simply substitute or set the function equal to 0. So to find, you could also use the quadratic formula, but for this particular function, that'll be overcomplicated. So to find the roots or the intercepts of the function, I'm simply going to write x squared minus 3x plus 2, and I'm going to find out when is that actually equal to 0. One of the biggest tools that we have for this is the principle of zero products, which says that if you know that the product of a times b is equal to 0, then either a is equal to 0 or b is equal to 0. So here, I can actually factor, because I know that there are two numbers that add up to plus 2, that multiply to plus 2, and that add up to negative 3. And that is negative 1 and negative 2. If you add negative 1 and negative 2, you get negative 3, and if you multiply them, you get plus 2. But now, by using the principle of zero products, I have that x minus 1 is equal to 0, or x minus 2 is equal to 0. So this equation right here is true if x is equal to 1 or x is equal to 2. So if x is equal to 1, we get 0, and if x is equal to 2, we get 0. Now that we have this, we have our interval. We have the interval from 1 to 2. So now we can check whether when you evaluate the endpoints, they're actually equal. So we have to show that f of a equals f of b. So this is what we want to show. Now, if we go back up here, what is f of x? F of x is equal to x squared minus 3x plus 2. Well, we just factor that. We factor that to be x minus 1 times x minus 2. This means that now I could actually plug in 1 into the factor version and see exactly what's going on. So if I plug in 1, I get 1 minus 1 times 1 minus 2. Well, 1 minus 1 is 0, and 0 times whatever, well, 0 times minus 1 is going to be equal to 0. And then if you plug in 2, you have 2 minus 1 times 2 minus 2. But this is also going to be 0 because this piece is 0. So 0 times 1 is 0. So now we can clearly see that f of 1 is actually equal to f of 2. So we have met all of the hypotheses of the theorem. We have that f is continuous on the domain, f is differentiable on the domain, and we have that f of a is equal to f of b on the open interval. Because we have met all of these hypotheses, we now know, we are guaranteed by Rolle's theorem, we know that there exists C in the interval 1 to 2 such that f prime of C is equal to 0. We actually know that this is true. Alright, so to find that particular C, we can solve the equation f prime of x being equal to 0. So to find this C, we simply solve this equation. Now, this equation has the derivative of x being equal to 0. Well, I don't know what the derivative of f is, so let's find it. F of x was given to be, again, x squared minus 3x plus 2. By the power rule, we have that the derivative of x squared is 2x, the derivative of 3x is, of minus 3x is minus 3, and the derivative of 2 is a constant, so that's just 0. So we know what the derivative is, which means that now this implies that I can actually write this as, I could substitute. Instead of writing f prime of x, I'm going to write what it's equal to, which means that it's equal to 2x minus 3 equal to 0. And I could solve for x. So I could add 3 on both sides. So I have 2x is equal to 3. Then I could divide by 2 on both sides. So I get that x is equal to 3 over 2. So Rolle's theorem right here says that if f satisfies the conditions of the theorem, there must be at least one point such that the derivative is equal to 0 when you evaluate it. There must be at least one point between A and B such that the derivative is 0. Right, so let me just quickly draw a picture of what this problem that we did represented. We had a parabola, so f of x was equal to x squared minus 3x plus 2. So we know how it's going to look. It's going to look like a smiley face going up. Now, we also know what the intercepts were. So we had an intercept at 1 and we had an intercept at 2. Because this is a parabola and the endpoints are going off to infinity, we know that down here the parabola looks like this, which means that we will have a minimum value here. Now if you were to take the value of c here and go down here, this is precisely where that x equals to 3/2 is. It's actually between 1 and 2. Now remember that I told you that the derivative being equal to 0 represented the slope of the line. So that means that the slope of the tangent line at this point is a horizontal line. So it looks like this. So this is what the theorem is actually telling us, because this is where f prime of 3 over 2 is equal to 0. Okay? Rolle's theorem is going to be very useful to us in the next coming sections. Right, let's do one more. So let's say you're given f of x to be equal to x to the fourth minus 2x squared, and that you are asked to find all values of x in the interval -2 to 2 such that f prime of c is equal to 0. Basically, we're asked to find all of the values between -2 and 2 such that the derivative, when you evaluate it at the point, is going to give you 0. Now, our interval is looking like this. We have a function. We don't know what's going on with the function because I haven't plotted it, but we know that what we're looking at is between the closed interval -2 to 2. Now, first thing you always want to do is, understanding the fact that we have Rolle's theorem now under our belt, is understanding the hypothesis of the theorem. So the hypothesis of the theorem says that if f of x is continuous and differentiable and the endpoints are equal, then we are guaranteed to have at least one value on this interval for which, when we take the value and we evaluate it in the derivative, we're going to get 0 as our answer. Now, f of x is a polynomial of degree 4. Because f of x is a polynomial, by the same thing as before, it is continuous everywhere. But precisely, it is continuous on the closed interval -2 to 2. Also, because f of x is a polynomial, it is differentiable on the open interval -2 to 2. Okay? So now all it remains to do before you can apply the theorem is show that f of b is actually equal to f of a. Now, how do we do this? Well, we take the function, which in this case is x to the fourth minus 2x squared, and we evaluate it at -2 and 2. Before I evaluate this function, I'm going to factor. It will make our life much easier. So let's see. I could factor from here x squared. So we factor out of here an x squared, I'm left with x squared minus 2. Okay? Now I can actually evaluate this at f of -2, which means that I have -2 squared times -2 squared minus 2. Well, that is equal to 4 times 4 minus 2. But this is equal to 8 because 4 times 2 is 8. Similarly, if we evaluate this at 2 now, we have 2 squared times 2 squared minus 2. Again, this is going to be 4 times 4 minus 2, but this is also equal to 8. So we have that f of -2 is indeed equal to f of 2. Now, by Rolle's theorem, because all of the hypotheses are satisfied, we know that there exists c on the interval -2 to 2 such that f prime of c is equal to 0. Now, to solve for this problem, again, we will look at the general function f of x equal to 0. Again, we do not know what the derivative of f is. We haven't found it, so let's actually take some time to find it. So f of x was x to the 4 minus 2x squared. If I take the derivative of this, of f, by the power rule, I have that the derivative of x to the 4 is 4x cubed, and the derivative of negative 2x squared is negative 4x. Now from here, we could actually factor a 4x out, so I'm going to do that right now. So I'm going to have 4x times x squared minus 1. And if you remember from college algebra, this right here is the difference of two perfect squares. So we can actually factor that as well. So this factors as x plus 1 times x minus 1. Now, why am I doing all of this? Well, because I have to find out when exactly this derivative is equal to 0. And again, this is what the derivative is equal to. So if I have f prime of x, and I want to find out when that's equal to 0, I can substitute here what f of x is actually equal to, f prime of x is actually equal to. That is 4x times x plus 1 times x minus 1. And once again, by the principle of zero products, I could figure out when each of these terms is equal to 0. Well, 4x equals to 0 whenever x is equal to 0. You could just divide both sides by 4. X plus 1 is equal to 0 whenever x is equal to minus 1. And x minus 1 is equal to 0 whenever x is equal to 1. So now we have that on the interval negative 2 to 2, the derivative is actually 0 at 3 different values of x. Okay, so we have that on the interval negative 2 to 2, the derivative of f is equal to 0 at 3 different values of x. Right? Rolle's theorem is going to be very useful to us as we move along in this term, especially with the application problems that involve the derivative that are going to be coming up soon. I'm going to end this part here, and next time, or the next section of the next part of this section, we'll be talking about another very important theorem that's going to be with us for a while, called the mean value theorem. Thank you for your time.